Hello class, this is a continuation of our discussion on general cylinders and cones. So we have a rectangular pyramid. To form it, we have this rectangular region, that's the base. And we have a point that's not on the same plane as the base, it's called the vertex. If you take the union of all the segments that you can form with the vertex and the base, you end up with this rectangular pyramid. And it has lateral edges that connect the vertex to the vertices of the base. And we have base edges here, which are the edges of that the rectangle down here. We also have something called the slant height, which is an altitude drawn from the vertex to one of the base edges. That's going to be helpful when we're looking at surface area. So we can generalize this notion, and we have something called a general cone. If the region, we can have the base be any region we want. And so you follow the same process, connect all the points to the vertex, put them all together, and we get a general cone in figure 2. So we name our general cones by the bases. If it is a disk, it's a circular cone. It's a polygon, it's a pyramid. And if we drop a perpendicular from the vertex to the base and it hits it exactly at the center, that's a right cone or right pyramid. If it's off center, like in figure 3, that would be oblique. And usually we use the term cone for a right circular cone. It'll be clear from the context what we're talking about. So I'd like you to try this example. I want you to name a lateral face and edge and explain how you know that you have a lateral face. So try that and I'll show you my solution. So if you look at triangle AVB in that region, so the interior as well, that would be a lateral face because it connects a base edge to the vertex. And there are 4 lateral edges. They each connect the vertices to the vertex of the pyramid. So we can also take cross sections of a general cone. They're going to be parallel to the base. What do you notice about the cross section and the base? What's special there? Let's look in GeoGebra. So here we have a pentagon as the base, so a pentagonal pyramid. And what do you notice about the cross sections that we're going to generate here? Well, they're all regular pentagons as well, and that's not a coincidence. So looks like we have a dilation. That is indeed what we have. So we can also have dilations in 3 dimensions. It's getting larger. It's enlargement, smaller to reduction. So we can see that here. I'm going to do an enlargement. It's going to be the same shape, but larger. If we go the other direction, the same shape, but smaller. So knowing that we have dilations, we can solve problems about the area. So let's see what's going on here. What can we say about segments A, B, and A prime, B prime? What's special about them? Well, since we have a cross section, we know that they must be parallel to each other. And as we previously learned, since they're parallel by our side splitter theorem and dilation theorem, we know that we have a dilation. So what can we say about these 2 triangles? So we can show that we have dilations that go between each pair of segments. So what's special about the base and the cross section? They're similar by side, side, side. And since they're similar, we can figure out the area. We know that to figure out the area, we have to have the ratio of the areas, and that's going to be the scale factor squared. So what's the scale factor here? That'd be 3 to 5. So we're going to square that. So that would be 9 to 25. And to figure out the area of the triangle, the triangular cross section, we're going to multiply the ratio of the areas times the area of the base. And they tell us over here that the area of the base is 25 square millimeters. So multiply 25 by 9/25, and we get 9, so 9 square millimeters. Now, like we said this before with a rectangle, let's do it with a right triangle. What do we get if we spin it or rotate it around one of its legs? What would we get with this rotation? So let's take this leg, for example. Well, we end up getting a cone in this case. If we do the rotation, let's look at it in GeoGebra. So here's our triangular region. And we're going to rotate it around this leg over here. And that edge is sweeping out to form the lateral part of the cone. If we cap it off with the base and we rotate this around, it is indeed the cone. So here we have the general cone cross-section theorem. I'd like you to read it to yourself and try to put it into your own words. Then I'll show you my solution. Here's one way to rephrase it. But basically, you could have any two types of general cones you want, and if the bases have the same area and same heights, you look at cross sections that are the same distance away from the vertices, no matter what the shape, those two cross sections have the same area. So let's prove that. So we're going to start off with our setup. We have three conditions. Area of the bases are the same, the heights are the same, and the distances from the vertex to the cross sections are the same. So we're going to call that distance h prime. So how can we show that those two areas are the same? Well, like we did before, we know how to figure out the area of B prime by using the area of B and the square of the scale factor. And the scale factor is going to be what we get if we divide H prime and H. Right? H prime is just the distance from the vertex to the cross section. H is the entire height. So we multiply that by the area of the base, and we can do the same process for the pyramid. So how can we say that these two are equal to each other? Well, these are almost the same, they just have different areas. But the areas actually aren't different. We supposed, in our hypothesis, that the area of the bases was the same. So these two are actually the same. So by substitution or transitivity, these two areas are exactly the same. So let's apply that. They give us here that BC is 3 times the square root of 2, B prime C prime is 2 times the square root of 3, and the area of this base over here is 30 square units. So what is the area of this cross section? Well, by the theorem we just looked at, we know that has to be the same as this cross section over here, and we can figure it out by using the scale factor squared, because that's going to be the same as the ratio of the areas. So to figure out the ratio of the areas, it's going to be B prime C prime divided by BC. It's like reduction. We're going to square that and multiply it by 30. And if you do that, you end up with 20. So you can put that in the calculator. I'm going to use parentheses here for everything correctly. You can do this by hand if you want to as well, but just showing you the proper way to put it in the calculator. Divided by 3 times the square root of 2. If you don't group things correctly, it's not always going to give you the right answer because it's going to follow order of operations. So if you don't group it properly, it's not going to do it the way you want it to. And we get 2/3, or 0.6 repeating. Multiply by that 30, and we get 20. So 20 square units. In these two videos, we learned the properties of general cylinders and cones. Thank you for watching these videos.